Good morning, good afternoon, good evening, good night, good whatever time it is where you are. Math Minute number 37. Let's do another Math Minute. The genesis for today's Math Minute actually comes from another video sharing platform. I won't say its name, lest the YouTube algorithm punish me. Yeah, I had a commenter ask me what was my favorite mathematical theorem, and this is something I've thought about for a while, as one does. And so I wanted to talk a little bit about the fundamental theorem of algebra. That is my favorite mathematical theorem. So I have a few equations in front of me here, and these are all polynomial equations. And the fundamental theorem of algebra has to do with polynomial equations. A polynomial is an equation that's generated using only addition, subtraction, and multiplication. So we have some unknown, our variable, and we're not in any danger, since we're only using addition, multiplication, or subtraction, we're not in any danger of generating expressions that can't be evaluated. We will always be able to evaluate polynomial expressions. This means that when we graph polynomial expressions, which I'll talk more about in a second, their domain is all real numbers. Again, any number we want, we can plug into a polynomial expression. In practice, what they end up looking like are a bunch of coefficients. They don't have to be real, but I'm just going to stick with real number coefficients. And then a bunch of different powers of x to the second, x to the third, etc. The fundamental theorem of algebra says that if you look at the degree of your polynomial, and degree can be defined several different ways, but it's basically the greatest power you see, at least if you're using a single variable. If you have more than one variable, you have to make a few adjustments, but degree is the greatest power you see in a single variable equation. For this first equation, that's obviously 2, and that's what we call quadratic equations. They're equations of degree 2. For this third equation, this third polynomial, you can see it's cubic, right? It has degree 3. Its greatest power is 3, and so the degree is 3. I'm just repeating myself now. Although we don't seem to have a power, there is technically a power here for this linear equation. We just don't write down the power of 1, but linear equations are polynomials of degree 1. What the fundamental theorem of algebra tells us is that whatever that degree is also tells us how many solutions to expect to the polynomial equation. So if I'm looking at a third degree equation, I should be expecting 3 solutions. Why this ends up working kind of requires that we have an understanding of a different mathematical tool called a coordinate plane. So think back to the 14th, 15th, 16th century. Mathematicians are super interested in solving equations. The height of mathematical sophistication is being able to solve equations, especially these polynomial equations. And along comes this guy, René Descartes, and René Descartes has this bright idea. He says to himself, well, if we could find a way to connect these algebraic equations to geometry, we could use insights from geometry to describe the equations, and eventually to describe the solutions to the equations. So he comes up with the coordinate plane, which is a way to track 2 different variables at once, the x variable and the y variable. And so if we look at an equation like 0 equals 1/2 x minus 3, rather than say 0 equals 1/2 x minus 3, where we're looking for the equation to return one particular value, we say y equals 1/2 x minus 3. And now that expression 1/2 x minus 3, any value it returns, we're going to place on a vertical axis. That's our y-axis. The x values we're plugging in to get those values become our horizontal axis, our left to right axis. And so if we plugged in, say, 0 for x, 1/2 of 0 is 0, 0 minus 3 is -3, and so 0, -3 is one ordered pair that's going to end up describing this equation geometrically. If you're familiar with slope-intercept form, you know that the next thing that happens is that we're actually able to track the way these ordered pairs change depending on something called the slope of the equation. So in this case, it's going to go up 1 over 2, up 1 over 2, and we can just connect all those dots, and there you have it. That is the graphical representation, or the geometrical representation, of the polynomial equation y equals 1/2 x minus 3. Now again, go back to why we were doing this in the first place. We're interested in solving equations. We wanted to know that particular value. When will that expression 1/2 x minus 3 actually equal 0? Since we replaced the 0 with y, what we want to know now is where will y equal 0? And that happens on the x-axis. And so for these equations, we end up particularly interested in where they cross the x-axis. That special point is what we call a root or solution or 0. Of course, we can also call it an x-intercept. That's what it is very literally, the intercept or intersection on the x-axis. In this particular case, you can probably tell pretty easily that it's 6. Half of 6 is 3, 3 minus 3 is 0. So the solution to that equation is 6. But as we get higher and higher degree polynomials, it becomes more more and more difficult to tell what those solutions are, or where they are, or really for that matter, even how many they are. And so again, that's where the insight of the fundamental theorem of algebra helps us. In this particular case, why would it be that a degree of 1, remember that's the degree here, even though we don't write it down, why would it be that a degree of 1 would make us expect one solution? For this, you have to think about degree in a new way. Degree is essentially a way to tell us about how often a function can change directions. A function of degree 1 cannot change directions, or it changes directions 0 times. So basically, once we start going, we're just going to continue in that direction forever. And so, of course, we would expect that if we start below the x-axis, at some point going up, we're going to cross the x-axis. Or if we start above the x-axis and move down, at some point we're going to cross that x-axis once. For a quadratic equation, or a polynomial equation with degree 2, that function can change direction once. And so what ends up happening here is you might start above the x-axis, go down, there's one solution, we cross the x-axis, we change directions once. Degree 2 means that we can change direction once. And then we come back and we cross the x-axis again. And so you can see we end up with 2 solutions to go along with the degree 2. For a cubic equation, we are going to expect that that third degree tells us we can change directions up to 2 times. You can probably tell by now the number of changes in directions is always 1 less than the degree. A degree 4 function can change directions 3 times. A degree 10 function can change directions 9 times, and so on. And so for this cubic, we might start below the x-axis, going up, cross the x-axis once, change direction one of our 2 times, down, cross the x-axis, change directions the other time, go back up, and there it is. We have 3 different solutions, 3 different points where we cross that x-axis because our cubic function can change directions 2 times. There are a few different things I love about this theorem. One of them is the fact that it's accessible to middle school students and high school students, which are the students that I work with the most. I mean, obviously we teach it to middle school and high school students, though I don't know that they always appreciate the various subtleties of the fundamental theorem of algebra. But even more than that, I think that they can appreciate its history and its development over time. It's also nice to recognize that whatever difficulties you're having with algebra, this was the height of mathematical sophistication 400 or 500 years ago. So we've got middle school and high school students doing what was the height of mathematical sophistication at that time. The other thing that I love about the fundamental theorem of algebra is it demonstrates the utility of being able to think about a problem in a new way. If we can take what was an algebraic problem, which we normally solve by manipulating symbols, but then when we run into difficulties manipulating symbols, translate that into a geometric problem, all of a sudden we can use all the tools of geometry and bring them to bear to help us find solutions on the algebraic problem. And that was eventually something that helped us come up with general case solutions for 2nd degree, 3rd degree, and 4th degree polynomials. It turns out, though, there actually aren't general case solutions for 5th degree polynomials or more, but I'll have to leave that for a future video. That's been your Math Minute for today. I think I'm going to be able to post this Monday or Tuesday, not sure. I hope you enjoyed that. If you have some questions, comment down below. What's your favorite mathematical theorem? Let me know, and that way I can study up on it and learn myself. I will see y'all next time.